Good afternoon, everyone. Just a talk about possible research in Namibia. This is actually the area we just downloaded now, LiDAR images, so you can see it's actually a flat area with a lot of sand, and of course a lot of wood accumulate when it rains. So this is the study area that I did my PhD on. Just to show you where Namibia is. So Namibia is, as you can see, Africa. Namibia is then located around here, South Africa, and then of course the other neighboring countries. You can see also Namibia is very, very dry. Here you can just see the desert, Namib Desert, and then also Kalahari Desert, and then of course, so you can see where most of the rain is here. Cape Town is here, also get nice rain, and then also nice rain, but Namibia is a desert, two deserts, and we are then getting rain from this area. The rivers goes down, because there's a lot of rain here, it comes down in rivers, and this is the area that is flooded most of the time because rain comes from the north. You can see that also the basin, so the rain starts here and then it comes down, and then most of the people in Namibia so most of the people in Namibia is living in that area. This is desert. The capital is in the middle here, and then there's a few people here, but most of the people are living in that particular area there. So just to show you again, the map of most people are here. You can see I'm from this town here, coastal town. Then we've got two coastal towns here. That's the capital, and then of course this is the study area, and then of course along the rivers there's also a lot of people, and those are areas. Most of these areas are desert. This is also desert. In this particular area there's a lot of mines where we have uranium. So that is our big national park where we have a lot of animals. So this is then the study area. This one is the national park, and then of course most of the rivers comes in from the area where there is a lot of rain from the north of Namibia. So the challenges we have, one of the challenges is there's not a lot of records. In most cases, hydrometric events like flooding, the patterns, the extent, the frequency, and the warning, because we have two countries. If you look at, we've got two countries, Angola here, they talk Portuguese, and then of course this kind of Namibia was German, so we talk German Afrikaans. So this one is then Afrikaans or Dutch. So most countries, so if we talk to them, there's quite a problem in communicating because of they are Portuguese, and Mozambique here is also Portuguese, and then of course Botswana, Zimbabwe, and Zambia, they all were British colonies, so we can all talk English together, but it's only them that talk Portuguese. So if there's flooding coming from there, usually there's quite a lot of challenges with communication, and because there's challenges with communication, it creates limited prediction, monitoring, assessment, and water resource planning. As you can see, also it's a big basin, and it's actually lack real observation stations. There's also, because of the desert, unreliable telecommunication. Some of the stations doesn't relay the information to the different networks, so it's quite problematic. And then of course outdated information is also the problem. And then of course there's no timely warning that floods are coming down. So usually what I needed to do then is this is one of the stations where we then receive information. I needed to then use this mapping device to map all of them out because some of them was not accurate enough. And this area usually is flooded, and then if the flood is here, then this area is underwater, and then of course we cannot access this area also well. So what I did in my PhD is then to produce this article, and as you can see again, what we want to do is this area here is the data that myself and Chris have downloaded now. So it's this particular area only there. There's a town in between, so the town is located approximately there. And then what I needed to do then is to understand, because as you can see, the river systems here is predicted from global evaluation data, and this is later data. So I've actually then verified whether this river systems and this ones, we can then find out which one is then the one in terms of the most dominant one. But most of them are almost 300 meters, very, very wide and very, very flat. So using later data, I was able then to either walk it and then also compare them with what is the most dominant channels in that particular case. So that's actually what we have done. What I also have done is then I've used then satellite data, trim the flying rain gauge. I also used the USAID satellite data for drought management, and then I also use another satellite image data, and then at the last one to see how does water actually go through the channels. And here you can then see I've used different rainfall on top, and then of course how each of this particular rain gauge perform in terms of the peaks. So you can see this is then the flooding peaks. There are a lot of rain accumulate, and then you can see the response of the flood to each of the particular peaks. And then of course here where we don't have then ground data, you can also still see whether if the rainfall is then accumulating here, then you can see there's a delay peak and then there's a lag delay peak. This is mostly because it's dry. If the water comes down, it needs to go in, infiltrate, and then multiple peaks is needed for flooding, and that's why it makes it also very difficult. Here, just data on just more information on this particular satellite images or satellite data that I use. So this one we also use for satellite-based discharge in runoff, which I use then in this red in blue one here. Most of the thing, as you can see, I've done a validation of satellite-based rainfall products over the dispersed area. I also modeled the discharge, as you can see here, and then also for flood hazard assessment using remote sensing and GIS, and we can also use it then for remote sensing and GIS health accessibility, and then of course non-source point pollution. So if you look at it, because most of Namibia's people are staying in this area, we can then use the channels to see where pollution goes, and then also understand from Angola down here how pollution and all these challenges that it comes with health can then be assessed. Then possible, this is also how it looks like. And as you can see, there's a channel, and you can see how the channel looks like. And then of course, usually if it's flooded, then the water goes until here, and it also goes under the trees to a particular side here. So possible areas is usually the study area is here, and then of course the area here we don't have data because it's in Angola, and it's quite difficult accessing this particular part. And then we also have a possible research area where a lot of rivers is connecting. Here we've got Zambia, we've got Zimbabwe, and then we've got the Chwana where all of them intersect there. So what type of research do we need? What we need then is, of course, to understand the dynamic of the channels in terms of the lateral migration or episodic vertical changes. So here, for instance, we need to understand how the erosion and sedimentation. So if the channel moves this way, it will deposit, and then next time it goes there, the next time we deposit here, and then it goes this side. So we need to understand over a period of time how the channel is moving, because how the channel is moving, flooding will then occur, depending on that. Also, what we need to see is that because of the flat surface, most of the water is flowed from behind, moving backwards. So we have got water moving actually in the opposite direction because of the channel integration on that particular flat area. And that's, of course, we need to understand in the short-term dynamics in terms of understanding the channels. What we also need to do is then to understand how, if the water fills up, how literally the water moves, and then of course correlated with our water level data, and then of course with weather data to understand the changes in terms of water depth, water extent, and volume of water in that particular area. Then of course also if we have instruments, we can then also look at the soil dynamics, and then of course the soil properties in terms of the texture and also the age, so that we can understand where the water and what type of how the sediments move in terms of their location. Also what we need to do is then, even though we only have data for small areas, we also need to understand, using the high accuracy DM, to understand then the properties of the other areas where the radar data is not available, specifically if we use the satellite data like SAR data to make sure that we understand, and then of course make a comparison with global data or flat terrain areas where we then can also make a comparison. And then of course also understand present day processes, sampling water for sediment support, and then water quality. Then of course also establish water meter sites. As I explained, it's very flat, and you will not be able then to do most of the measurements. Instruments can't be installed. And then of course myself and Chris was talking about this, which we will then also want to use using the historical aerial photos to generate the SMI data on that particular one. So most of the global data, as you can see, it gives errors. So you can see here, for instance, this is a flat area, but if you look at the landscape, for instance, from that point to that point, you can see it gives you then elevations like that. So to correct this one is quite a problem, because this is then also because of the flatness of the area, and then of course of the return of the signal to the satellite, which gives you then errors like this in a flat area, which we then need to correct, and to make sure that we then have the corrected. Then of course we soil carbon afflux and carbon storage. We can also use flaring before and after comparison, digital evaluation models, as I mentioned. Look again closely at satellite-based rain stations, and then disaster reconstruction using aerial photos and then DFS. Aerial photos is available from 1910 to approximately 2010. I think it's been taken every 10 years, so hopefully we get a full range of data that we can then do research with. And then of course also, if it floods, it looks like this, so you can see the road is then lifted, so that also creates then water moving backwards, and flooding then occur because most of the road infrastructure is too low, and then they need to then lift it up so that it actually causes more flooding than the topography. So that's in short possible research in Namibia and how Namibia looks like. So if you're interested in that, you're welcome to contact Chris and myself, and we can then look at some sort of way how we can work on possible research. That's all. Any questions on it?
Thank you. ナミビアと日本の大きな違いは、向こうほとんどデータがないから、人工衛星データがさっきから見せてた雨量データみたいなの全て人工衛星から作ったデータですね。いくつかの雨量計があるんですけれども、その雨量計と人工衛星データを合わせて、で他の場所をどのぐらい雨が降るとかいろいろ調べて、また地形データのところも衛星データ以外もほとんどないから、一回ライダーデータが、私が使ってるライダーデータとは非常に精度が高い地形データを作れたんですけど、それ以外は全然ないので、だからあそこで研究するのがもう面白いですね。すべてやったらすべて新しいですね。でその水害が毎年起きてるから、水害の問題で彼が今日お話ししてくれたんですけれども、その水害関係で何が研究やりたければ、人間やりたければ、それぜひ私もサポートになりたいと思います。水害とかその自然災害とまた環境問題にもつながっている。彼が話したところで思うのが、水の多い分がモンゴラから来てるんですけれども、水がいろいろ汚いから、実は水の中に何が入ってるとか、それも調べる必要もあるとお話しして、他のお話もしてるんですけれども、もし興味があれば、ぜひ一緒にやったらいいなと思います。で、さっき話した通りで、実はブラダック先生がもうアフリカにすごく行きたがりそうで、もうそこで研究もやりたいとお話ししてたから、今回そのチャンスもあるので、もしかしてもうブラダック先生と一緒に研究もできたらいいなと思っているので、ぜひ頑張ってください。マスターに行く学生たちとか、それも見てもいいと思います。実はナミビアは1993年かな、覚えてないかな、このぐらいの時にできた国なので、その後に日本が確かも抱いたんですけれども、他の国と同じでいくつかの研究プログラムもあるし、また学生のためのプログラムがあるんですけど、ナミビアではなんか一つの大学しかないんですよね、フランスさんがいるのところで。ナミビアに研究しに行く人たちまだ少ないし、逆にナミビアから来てる学生も少ないので、実は予算もあるので、今回その日本確かの予算を使ってブラダック先生が向こうに行けそうな感じのお話もあるので、あれたちもそれもそのシステム利用ができたら面白い研究できるかもしれない。日本より結構エキゾティックとか面白いことが絶対あると思いますので、興味を持っている方があったらお願いします。Thank you very much, Franz.
Okay, thank you.